So let's look at how to compute a transition matrix. So we'll look at this system that we looked at before, and we already worked out the eigenvalue-eigenvector pairs for this matrix. We've got an eigenvalue of 2 with vector 3, 2, and an eigenvalue of -5 with vector 1, 3. And so we're looking for the transition matrix e to the at, and we know that we can find it as the fundamental matrix times the inverse of the fundamental matrix evaluated at 0. So we've got, for this matrix, we take the fundamental matrix as 3e to the 2t, 2e to the 2t, e to the minus 5t, 3e to the minus 5t. And so then when we look at x of 0, this is going to be 3, 1, 2, 3. And so x of 0 inverse is going to be 1 over the determinant, and then you swap the places on the diagonal, which doesn't do much, and negate the off diagonal to get this one. And then your matrix exponential, or more precisely your transition matrix, is going to be, I'll put that scalar 1/7 out in front because I can put it anywhere, 3e to the 2t, 2e to the 2t, e to the minus 5t, 3e to the minus 5t times 3 minus 1 minus 2, 3. And so working out this product, we get 1/7 9e to the 2t minus 2e to the minus 5t, 6e to the 2t minus 6e to the negative 5t, minus 3e to the 2t plus 3e to the minus 5t, and minus 2e to the 2t plus 9e to the minus 5t. So there is our transition matrix. So then what if A is defective? So in this case, you don't have a basis of eigenvectors, right? So we need to resort to finding generalized eigenvectors. So let's have a look at an example. So perhaps we've got the matrix 6 minus 8, 2 minus 2. And so now for this one, the eigenvalues are both equal to 2, and the when we go looking for an eigenvector, we end up with 2, 1, and so the situation is defective because we only have one eigenvector for an eigenvalue of multiplicity 2. So we look for a generalized eigenvector. And so let's see. So we're going to look at, we're going to be solving a minus 2i x equals, or maybe I'll call it v, equals v1, this one that we found in the last, well, that I already found without working out the details. So let's see. So if I subtract 2 off the diagonal, I have 4 minus 8, 2 minus 4. And then we drop 2, 1, our previously found eigenvector. That's the augmented part there. And we row reduce, and we find 1 minus 2, 1/2, 0, 0, 0. And so then that tells us that we have a to 1 minus 2t is equal to a half, and a to 2 is free. And so we can take our generalized eigenvector to be 1/2 plus 2t, t. And so this is the same as t times 2, 1 plus 1/2, 0. And so now we see where we have, so our v1 is back. And so here's our v2. All right, so our solution is then going to be c1 e to the 2t v1 plus c2 e to the 2t, and then we've got tv1 plus v2. And so this is the same thing as 2e to the 2t, e to the 2t. And in the next column, now we've got 1 plus 4t e to the 2t, and 2t e to the 2t. And then this is going to be times our vector of constants c1 and c2. So that's what our fundamental matrix looks like for this defective example here. So evaluating this fundamental matrix at time 0, we get 2, 1, 1, 0. And finding its inverse, we have 1 over the determinant times, and then we flip the diagonal and negate the off diagonal. And so our transition matrix is going to be, whoops, I messed it all up. It is going to be this one here times -1 times, actually, you know what, I'll just incorporate the -1 into the entries since we've got some negatives in there. And then multiplying this guy out, I get, let's see, I'll bring the e to the 2t's out in front because they're everywhere. And then I'll have 1 plus 4t minus 8t, 2t, 1 minus 4t. So there's our transition matrix for this defective example.